Hello everyone and welcome to this lecture. Today we are going to interpret the divergence of a vector field, and we are going to do that through an example. And in this example we are going to see the application of the divergence operation. So let me first draw something. Let me first draw a tube, an almost cylindrical tube which has an opening like this, which is not cylindrical. So this is our tube, and inside this tube we have some water that's flowing. So this is our water, and this tube will have a cross section of, let's say, A prime, and the outer surface, that is the opening. So let's call this side opening. This will have a cross section as denoted with A. So, and this green lines, they represent our fluid flow, or let's say the water flow. So this is our water flow. And let's say our water is moving at a velocity v. But we can make it more interesting by saying that this v is dependent on x, y, and z. So v is actually a function of x, y, and z, but we will just denote it like v. We won't write the x, y, z explicitly. So now let's say you are considering some water up to this point, let's say from here to here, and let's say this is point A, this is point B, and this is some distance L. But our velocity is not dependent on time. So within this very small length, we can take this velocity to be constant, and we are going to say this L over here, this L will be Vt. It takes some time from going to A to B, and that is the time that is indicated over here. And we are interested in calculating the mass of the water first. So the mass will be m, will be rho, that is the density of the water, times the volume. So let me use it at capital V. And this volume is nothing but the cross section, that is A prime, times the length. So we are going to write it as rho capital A prime V and T, like this. Now let's say you have this chunk of water over here, and this water is gonna flow through all the way and come out from here. So we also want to see what happens, that is how much of the water, or the proportion of the water that comes out of this surface over here, that is indicated with A. So now what I'm gonna do is that I'm gonna draw a normal, unit normal vector to the surface. And if you recall that the unit normal to A prime is like this, so the direction of A prime is just like this, and the direction of A is along this n hat line, that is the unit normal, and they have some angle between them, right? So you can write now that your A prime is actually A cosine theta. So let's replace that. So it will be, and we're going to replace it over here on this equation, and it will be a, instead of a prime, now you will have a vt cosine theta, and this is the mass, right? But a useful quantity when we are considering a fluid flow is to consider the mass per unit area per unit time. This is also known as the flux. So this will be just rho v and the cosine theta, right? And let's call this quantity, this rho v over here, and denote it with phi, some phi. So this will be phi cosine theta, and this will be useful for the things to come that I am going to talk right now. Since we are considering a fluid flow through a tube and it's a three-dimensional thing, we can also extend our argument and we can consider an element. So let me write it down. Now we consider an element that is a rectangular shaped box in 3D space. So if I try to draw that, it will look something like this. This is our coordinate axes, this x, y and z, and or obviously you can change it as long as the right handness of the coordinate system is preserved. So let's call this as the z-axis, this is our x-axis, and this will be the y-axis. And now we want to draw the box. So the box looks something like this. Right? And let's call one of the surfaces that lies between y and z as 1. So this marked surface is called 1, and the other marked surface like this is called 2. Okay, and if you think that these lengths are actually very small, so you can call it as dx like this. Similarly, this part over here, this will be just the dz, that is this one, this is dz, this is dx, and this perpendicular part will be dy. And we are going to consider the same fluid coming over here from all directions and going out. So this is in and this is out. So as these dx, dy, dz are very small, what we're going to do is that we're going to consider how much fluid is coming in. If we consider the first surface that is denoted with 1, we want to see how much of the fluid goes out from the second surface. And this is where the divergence will come in, as you will see very soon. So we want to consider surface 1 and 2, 1 and surface 2, because they are opposite to each other. And now we want to see how much of the fluid goes in and how much of the fluid goes out. So we can calculate the loss of the fluid. That means if the fluid gets stuck inside this surface, we can calculate that. So if you recall that we denoted some v over here, this capital this phi over here, that we denoted as rho and v, right? So now we consider for this surface 1 and surface 2, and since we are considering the fluid flow or the water flow throughout this volume, and we already denoted this phi with rho v that was associated with this mass flow per unit time per unit area, and obviously there was a cos theta because these two areas they had some angle between them. And here we will consider where the theta is 0. That means the velocity vector and the area vector will coincide. So we are now considering for surface 1. So for surface 1 we want to see the fluid flow. So the flow per unit area per unit time is simply phi, right? But phi is a multivalued function, and since you can see that when the fluid is going through this surface 1, it's actually pointing out the x component. That is, we are considering the x component since it's going through surface 1. So we need to find the x component of this phi. So the x component of this phi will be denoted with phi of x, and it can be easily obtained through the dot product with the unit vector along the x-axis. Okay, and this is fluid flow per unit area per unit time. So fluid flow per unit time is just phi of x. Obviously this is through surface 1, so surface 1, this will just be dy phi of x dy dz, right? Because the area for surface 1, let me call it S1, is just dy dz. Okay, and this is the fluid flow per unit time, and obviously there will be a fluid flow per unit time from the surface 2 like this. And again we will consider that the velocity vector and the surface area vector will coincide, so the cos theta will be 1, that means theta is 0. However, since this phi is a function of x, y and z, that is phi is a function of x, y and z, for surface 1, if we denote it by this phi of x, y and z, for S1, for S2 we need to consider phi of x plus del x, y and z, because look at this, the difference between surface 1 and surface 2 is just del x or dx, whatever you want to call it. Let's call it dx just to be just to agree with our graph. So, and the y and z coordinates are not changing, so after we do this, that is for surface 2, we want to have this phi of x plus del x thing dy dz, right? And now we want to have the difference, and if we take the difference and we require that this difference, that is difference is just, this is the thing we're requiring, because if you recall that we were talking about, we want to see whether the fluid, how much of the fluid gets lost in the volume that we are considering. So this difference is just 2 minus 1. This is our claim, or so to say we are requiring this thing. So this is phi of x plus dx minus phi x. We can factor out this dy dz. However, you can see that since this dx is very small, what we can do over here is that we can divide it by another dx over here and multiply with the dx over here. Actually, this is not the formal procedure. The formal procedure would be to, instead of writing dx, you can you have to go for the delta thing. That is, instead of dx, you want to have this delta x, and then you take the limit of delta x, that will go to 0, and that should give you the dx. So this is the formal thing, but since we're doing it a bit informally, so let's carry on with this. And now we say that limit dx goes to 0. This seems a bit weird, but this delta d, it doesn't matter. You just have to stick with the notation, because we want to see what happens in the infinitesimal area. So this means we are making this dx smaller and smaller and smaller as much as we can make it. And this is exactly the partial derivative of phi with respect to x. And here you will have this dx, dy and dz. This is the difference between these two surfaces through which the fluid is flowing out. And a similar analysis, let's call it equation 3. A similar analysis for the other surfaces, that is this top one, bottom one, top and bottom, this one and this one. They will give us the following. That is, through the top and bottom surface, we will have this del phi y by del y dx dy dz, and through the other two sides we will have del phi del z dz dx and dy. And finally we want to add these things, that is, if is equation 4, let's say this is equation 5, we want to find out finally the total loss of fluid. And to find the total loss of fluid, you just need to add these three. Okay, this is easily recognizable, because you are in these 3 steps you are calculating the loss of fluid for a particular direction, and finally you just need to add them. So if you add them, you end up with this expression. And if you see that this phi and this expression that you are seeing over here can be written as the divergence of the vector field times the infinitesimal volume of that cubic region or the rectangular region in our 3D space. So why am I calling this phi a vector field? Why? What justifies to do that, right? Because if you recall that we denoted our phi with rho v, but v itself is a vector field because it's a velocity field, and we also use that concept over here where we took the components of this phi field. So this divergence and this infinitesimal volume, when multiplied together, they give us the total loss of fluid. So if I say total loss of fluid divided by the volume of interest, that is the volume you are considering, most of the time this is an infinitesimal volume, is just the divergence of the field phi. But remember, phi was defined as rho v, where v was a vector, so I'm just giving these arrows right now. So, and rho is a scalar, so you can bring out this rho and you can write it like this. So this is the physical application or the geometrical interpretation of divergence. It tells you how much of the fluid is actually diverging out. Okay? Or if you want to speak mathematically and you don't want to refer to a physical velocity field or something like that. It says how much of the vector field is either diverging, or is it converging to a point, or is it diverging away from some point. So it gives you the idea of a source and a sink. So source and sinks. So let's say you have some field that looks like this. If you denote the field with these arrows, it looks like this, and this field is probably familiar to you. This is just the inverse square field. Obviously the drawing is not up to scale, but this is a diverging field, and it has in fact a positive divergence and indicates towards a source. So there is some source over here that has some influence in this region, and if you take this source to be, let's say, a positive charge, and you put another positive charge over here, it will repel it, and this will follow the paths that is indicated by these arrows. So this has some divergence. And let's say you have some field like this. Let's say there is a field that that points towards some point over here, and this is something we call a sink. So it's like everything is converging towards that point. So if a vector field has a divergence positive, then you can easily say that this is going outward from the origin or the source or the point of interest. And if it has a negative divergence, you can say that there could be a sink as well. But note that if a field has divergence, it does not mean that that field doesn't have a curl. You might have a field like this that's diverging and also curling, like a spiral. Okay, and I prepared some demonstration, and let me just show that to you. So as you can see, this is a figure and this is a vector plot, and these arrows are actually diverging from some source. And also if you notice these edges, you can also see that it has some tendency to curl as well. So for a vector field, divergence and curl can coexist at the same time. So that's an important thing. And here I have plotted a two-dimensional plot, and you can see that all the arrows are pointing outwards. So this is also an example or a visual representation of positive divergence. So in summary, what I can tell you about divergence is that it actually measures the tendency of a vector field to spread out, or whether it's trying to converge to a point. So this will be it for today, and thank you.